Hello, I'm going to talk to you today about a resource allocation problem that has a very interesting solution called the water filling solution. Before we get to the problem and the solution, let's think about the following scenario. You have exams coming up in 2 days, and let's say you have about 15 hours that you can study for your exams. So you're taking 3 courses this semester. A typical decision that you have to make at this time is to decide how you are going to spend these 15 hours between studying for these 3 different exams. Now, the marks that you get in these exams depends on how much time you study for these exams, right? Now, this is a particular example or an instance of a more general optimization problem called a resource allocation problem. So typically in these cases, you have a resource that's fixed, which in this case was like 15 hours. Time was your resource. You have a resource that's fixed, and you can allocate your resource into many tasks. Each task gives you a certain reward, and what you want to do is to maximize the total reward that you get. But you have a constraint that the total amount of resources that you can allocate to these different tasks is fixed to be P, right? So the optimization problem we are interested in is in maximizing the sum of the rewards, sum over I of Ri, and the constraint you have, so you want to maximize this subject to the sum of the resources that you allocate to the different tasks being fixed. Now, to solve this problem, we first have to understand how the reward is related to the resource that you allocate to a particular task, right? So for example, what is the relationship between the marks that I get for in subject 1 as a function of how many hours I study for that subject? So this is typically captured through what is called as a utility function or as a reward function. So a typical reward function might look like this. So if you plot the resource that you allocate to a particular task, P sub I, and you think about how the reward changes as a function of P sub I, a typical reward function would exhibit a characteristic like this. Now, you may have heard of people talking about diminishing returns, so on and so forth, and this is showing something similar to that. So let's think about this point. So what that tells you is, if you allocate 0 resource to a particular task, you're going to get 0 reward. If you don't study for an exam, you're going to get 0. However, as you start to spend more time on a subject, your marks increases, right? It's going to increase rather quickly initially, which means there is going to be a big difference between not studying for a subject at all and studying a few hours for a subject. However, the additional marks that you are going to get as you spend more and more time, there's going to be a lot of diminishing returns. It's not going to increase as rapidly as it did in this part of the curve. So you will have to study a very large amount to increase your score from 90 to 100 or 90 to a 95 rather than increasing it from 0 to 5, right? And this is not only true when studying for exams. Many reward functions show this kind of behavior. Another classic example is happiness versus amount of money that you spend on different activities. So for example, if you think about happiness that you get from buying a house, I mean, there is a big difference between not having a house and having a house, even a small house. But once you start to live in a small house, the extra happiness that you get from living in larger and larger houses is substantially smaller. I mean, the same thing with when you spend money um, for eating, right? There's a big difference between being hungry and getting a little amount of food, but the extra happiness that you get from eating at better and better restaurants or more and more food is definitely diminishing as you ha- start to have little bit of food. So this kind of a reward function is what we are going to be interested in. And mathematically, a good, we're going to focus on one particular reward function. This reward function is going to be given by log of 1 plus pi over gamma I. So gamma I here is a parameter that tells you how the reward that you get for a particular amount of resource is related to the amount of resource that you spend on the task. So for example, if gamma is small, then it means you get more reward for a given amount of resource. If gamma is large, then you are getting smaller reward for the same amount of resource. So in terms of the example for studying for an exam, what this might mean is you may not be equally good in all the 3 subjects where you have exams. So if you are very good in subject 1, then this would correspond to gamma 1 being small, because even a little bit of time that you spend is going to increase your marks substantially. And if you're not very good at one of these subjects, then your gamma is large. You need to spend a lot more time to be able to make the same amount of marks as in a subject that's easy for you. Okay? So now for this particular reward function, we're going to see how to solve this optimization problem. How should I allocate my resources pi so that I maximize the total reward that I get, given that I have a constraint on how much time I can spend studying for the exam. I'm not going to tell you how to solve this optimization problem in this video. I'll make a separate video for that. But I will discuss what the solution to this optimization problem is. So remember again, these gammas are the factors that decide how the reward is related to the resource. Now, the solution can be understood like this. Let's say we take the gammas and we sort them in increasing order. So we say we have gamma 1 is less than gamma 2 is less than gamma 3. And think of constructing a water tank. Suppose I construct a water tank which has 3 compartments. It has 3 compartments. The floor in the first compartment of the water tank is at a height of gamma 1 from the bottom. And in the second compartment, the height of the floor is gamma 2, and the height of the floor in the third compartment is gamma 3. Okay? Now what the solution tells you is this. Let's think of pouring water into this water tank, and we're going to pour p liters of the water into this tank. So let's think about what would happen if you have a very little amount of water to pour into this tank. I'm going to pour the water from here and assume that the laws of physics work so that the water will flow to the bottommost point in the tank. So if I have only a little bit of water to pour, what's going to happen is all that water is going to go into this compartment, right? So what that means is if you have only a little bit of resource, you want to put all your water into that task that gives you the largest reward. So so let's say I pour water and the water stands up to this point, then what that means is this is the total amount of water that I poured, and I'm going to pour all of that into my first tank. But as the amount of resource increases, which means as the amount of water that I have to pour into the tank increases, what's going to happen is at some point the water is going to come up to this level in the tank. And what the solution says is, that means you should put this much resource into task 1 and this much resource into task 2. So notice that the height of the water is constant in both the compartments. So what that really tells you is P1 plus gamma 1 must be the same as P2 plus gamma 2. So you want to pick your piece such that P1 plus gamma 1 is the same as P2 plus gamma 2 as long as P1 and P2 are positive. So you want to put enough water into this compartment that stands up to this level, and the water in this compartment stands up to this level, right? Now, and then if you have even more water to put, what's going to happen is this water is going to now go into all three compartments, and the same thing is going to happen. So the water will go up to some level here, and this is the amount of resource that you want to put into task 1. This is the amount of resource you want to put into task 2, and this is the amount of resource that you want to put in task 3. So again, notice that the solution says Pi plus gamma I must be a constant. Of course, I will derive this in the next video, but that's basically what the solution says. And let's think through this a little bit to see if that makes sense. Again, gamma 1 is the task that, or rather in this case, task 1 is the one that gives you the best reward for your resource. So what this tells you is, if you have only a little bit of resource, put everything into task 1. But once you have reached more than this level, it's better for you to put your resources into both task 1 and task 2. So notice that it doesn't tell you put all your resource into the task that gives you the largest reward, right? And that makes sense because the reward function is something that shows diminishing returns. There is no point in putting a lot of resource into any one reward, any one task, because the reward that you get is decreasing as the amount of resource increases. So it's better for you to split it into 2 tasks beyond a certain point. And indeed, this would make sense because it's no point in just putting all your resource into studying for one class. But if you had only very little amount of time to study, what it tells you is just study for the one class that's going to give you the largest marks. Okay, and so on and so forth as you go along. And I think that's why it's called as the water filling solution. And you might wonder why an engineer like me is actually interested in reward and resource and in what seems like this is basically economics. Actually, it turns out that there is the mathematical problem that I'm interested in wireless communications is actually is very similar to a resource allocation problem that people in economics are interested in. For example, the reason we are interested in this problem is we try to design communication systems. So it turns out that in many cases, when you try to communicate with your cell phone, you have an option of communicating over many channels. Each channel has different amounts of noise, and you have a total fixed amount of power that you can put into these 3 different channels. And the question we are often interested in is in figuring out, how much power should I put into each one of these channels so that I maximize the total amount of rate that we can get, data rate that we can get. I mean, you're all interested in using as little battery as you can to get as large data rate as possible so that you can stream your Netflix, right? And so in this problem, it turns out that if I put in a power Pi into my channel, depending on how much noise I have in the channel, the amount of data that I can get, data rate that I can get from this channel is actually related exactly through this expression. It turns out to be exactly log of 1 plus Pi over gamma I. And this is what your Wi-Fi uses to decide how to split its data into multiple channels that it can split it into.